Okay, so I guess we'll get started. We might have some more people trickling in, but that's okay. Also, quick reminder to everyone that our seminars are available on our YouTube channel. So if you missed some of our previous iterations, you can catch them all there. Um, Welcome everyone to this month's online seminar of the Working Group on Active B-stars. Today, it's my pleasure to introduce Dr. Abel de Burgos Sierra. Abel is currently an ESO fellow down in Santiago, I think also working on Paranal. But previously, Abel actually has quite an extensive experience in observing, having worked at La Palma on the Isaac Newton telescope and the Nordic optical telescope. And then did his PhD in the Canary Islands under the supervision of Sergio Simandias and Miguel Urbaneja. So we're very lucky to have Abel today with us to talk about the terminal age main sequence of massive stars. So Abel, without further ado, I'll let you take it away.
Thank you, Alex, and thank you one more for letting me present this result. And hi, everyone. Good morning or afternoon or evening, depending on where you are on this planet. Yeah, today I want to present some results that were recently accepted for publication in Astronomy and Astrophysics. Under the title, New Clues on the Location of the Terminal Age Main Sequence in the Massive Star Domain. And this work has been done in collaboration with my PhD supervisors, Sergio Simón Díaz and Miguel Urbaneja, together with Gonzalo Holgado, Silvia Ekstrom, María Ramírez Tanos, and Eleonora Zari. Now, for some of you may have already asked the question, like, okay, but don't we, from the title, like, don't we already know where the terminal age main sequence is in massive stars? So then stay tuned, because this is what is going to be the topic of this talk. So just to bring a couple of things for background or context, traditionally or classically, massive stars, or most of the massive stars, are considered to be born as O-type stars, and they remain as O-type stars through the main sequence phase. Then once they complete this phase and they leave the main sequence, typically they are considered, or they turn into B-type stars, typically B-type supergiants. Or in other words, B-type supergiants are considered, or classically considered, as post-main sequence objects. Now, this on the book now, but in order to test this, to check for this, we need to find empirical evidences. So that basically we need to answer, how can we observationally locate the end of the main sequence? So we know from theory that stars spend most of the time in the main sequence. Then after the core hydrogen exhaustion, before the ignition of the helium burning phase, the stars suffer a rapid reconfiguration. They have their envelopes expand. They become significantly cooler in a short period or short periods of times, producing what we popularly know as the Hertzsprung gap. This would translate into a drop in the number of stars that we see in this transitioning region. So I made, to illustrate this, I made this HR diagram, Hertzsprung-Russell diagram, where I am showing the models from Geneva and MESA for no initial rotation and solar metallicity. And I have put evenly spaced in time or age points. So it means that after you see all these points here, which correspond to the main sequence, but then once the stars leave the main sequence, we wouldn't expect to have many of these stars here, which, well, I have illustrated where's the location more or less of this Hertzsprung gap. So this is the question we want to answer. Do we have stars here or we don't? So if we trace it all the way back to the 1990s in the work by Fitzpatrick and Garmany, using observations for more than 1,000 stars in the Large Magellanic Cloud, this is the picture that they found. So first of all, they found like a very large number of objects located beyond the theoretical end of the main sequence. And also many of these objects were actually B-type supergiants. So basically this brought a big issue into our understanding of massive stars. This was actually referred to the terminal age main sequence problem by Langer in 1992. Back then, they argued that one possible explanation of this is that these B-type supergiants were actually coming from a post-red supergiant phase, but it was, I mean, quite challenging to explain this overdensity with this argument. Some other researchers were also accounting for binaries to populate this. If we move forward in time and we go to, which is our reference work of our work, which is the one done by Castro et al. In 2014, this is how the situation looked like. I mean, evolutionary models were updated, and also the sample was also upgraded with new observations. In this case, I'm showing not an HR diagram, but the spectroscopic HR diagram, which uses the spectroscopic luminosity, which is defined as effective temperature to the fourth divided by the gravity, as a proxy of the actual luminosity when you don't have the distances. So you can get the regular HR diagram. So we see that the stars that they use in this work, which are represented here with this shady or this mesh in gray color, are actually, well, their location agree quite well when we go to lower masses within massive stars. So for masses between 9 to 15 initial solar masses, the agreement between the empirical data and the theoretical, or the location of the empirical terminal main sequence and the theoretical one, it's more or less quite good. We actually see this lack of objects. And then as we go to higher masses, then the situation becomes not so nice. We start to see discrepancies between 15 to 20 solar masses, and then it becomes a real issue when we go above those masses, because we don't clearly see, I mean, it's really hard to say where is this end of the main sequence, right? So this was the situation back then, but I want to dig a little bit more into what they did back then. They used a sample of around 400 OB and A-type stars, plus another 150 F-type and cooler spectral type stars. And these stars come from many different works. From results, they basically collected results from other studies, and I have listed them here. So many different studies, each of which were targeting a specific group or different groups of stars. This is problematic because, of course, when you are targeting a specific group of stars, you may have holes in your HR diagram, or you may have overdensities in your HR diagram. So this is one important issue. Then another issue comes from the fact that, of course, each of these works were using different techniques. Maybe they were using calibrations for the temperature. Maybe they were using some atomic models that other people were not using, or were using different ones. So this would also cause like an inhomogeneity in the results. I already mentioned it, but they were not using the distances, either because they were not available or reliable. And therefore, this is not the actual HR diagram to compare with evolutionary models. And also gravities are not corrected from centrifugal forces, which applies to the fast rotating objects. And therefore, I mean, if this correction would be applied, then some of these stars would go downwards in the spectroscopic HR diagram. So bottom line, these are heterogeneous results, very heterogeneous results. But it was the best that they had back then, which is perfect. Bravo to them. Like, it was actually the best that we had. Now, there are two things that I want to mention regarding biases when constructing samples to compare with evolutionary models. One is biases that are produced by the intrinsic brightness of the objects. So if you have an observing facility, a telescope that can observe down to magnitude, say 11, at its our case, and you say, okay, I can only observe stars that are brighter than magnitude 11 in B, then you're going to target more stars of one specific spectral type than the others. In this case, you would target more like late B type stars and A type stars than early B or O type stars. So this will, of course, create biases, because if you are observing more stars that are of one specific spectral type just because they are intrinsically brighter, then you may think that the end of the main sequence is at a temperature that it's not there. It's just like you have more stars than you should in that specific temperature. And there's also biases due to the extinction, which is the other thing that it's important to take into account. And we made this this plot in 2023, in which we are showing the apparent visual magnitude of different massive stars with different spectral types and luminosity classes against the distance. So of course, as you go to further distances, stars become fainter, but then you also have to count with the extinction. So the point here, or the key thing, is that you are going to be biased by stars that are intrinsically brighter, and you are going to start losing stars that are intrinsically fainter. We know that, I mean, there are some cases in the galaxy that even when you go up to 2 kiloparsecs, there are few stars that have been already detected with an extinction of even 5 or 6 magnitudes. But if we want to, and this is applicable to what I will show you after, if we want to target this upper part of the HR diagram, we would look for like supergiants. And then, for example, up to 2 kiloparsecs, we can afford, if we are limited to magnitude, say 10 or 11, we can afford like to have 5, 6 magnitude of extinction. And in principle, we shouldn't create biases, or if there are some, I mean, we would miss a few stars, not many. So given these two things to also take into account, we jump into our sample, the one that we used in our study. So we wanted to create the largest and possible sample of O and B type stars that has to be homogeneous and with the highest possible degree of completeness. So for this, we use the IACOB spectroscopic database, which gathers spectra from 3 different facilities: the Nordic Optical Telescope and the Mercator Telescope, both of which are in La Palma, covering the Northern Hemisphere, also a little bit of the Southern Hemisphere. And then the MPG ISO 2.2 meter telescope in La Silla to cover the Southern Hemisphere. All these facilities, they provide high resolution spectra. We observed stars at high signal to noise ratios, and they also cover a wide range of wavelengths. In total, or as it is right now, we account for around 18,000 spectra of more than 2,500 galactic O, B, and A type stars, plus an additional number of 2,000 spectra of around 500 stars gathered from the ISO archive or from collaborations. So in total, we have observed around 550 O-type stars and 900 B-type supergiants, which are the ones, the objects that are interested for this particular study, because it's in these spectral times where we want to find clues on the end of the main sequence. You have the distribution of these stars in this radial plot here around the solar neighborhood, and you can see, well, we reach magnitudes, I would say up to or down to 11, and for distances of up to 4 kiloparsecs. Then from this sample, we provide reliable, or we have obtained reliable parameters, spectroscopic parameters, and distances, masses, luminosities, for 300 O-type stars and around 550 B-type supergiants. So the difference is because not all the objects have been analyzed. I mean, the methodology that we used allows us to analyze only down to B6 spectral types, so we are missing the later spectral types. We're also excluding classical B-type stars and, well, general stars that have strong disks. We also exclude double-line spectroscopic binaries, or SB2, because we have not done spectral disentangling yet. And we also excluded hypergiant and a few other problematic cases. Now, here's the point. What we want now is to see which is the completed level of this analyzed sample with respect to the massive stars that are out there that we should, in principle, account for. And for this, what we did is to use the ALMA Luminous Star 3 catalog, which is a catalog developed or created in Madrid by Miki Pantaleoni and Jesus Maiz Apellani. And they collected, or they created this catalog. Well, this is still has to be published, it's in preparation, but they created this catalog that can reach magnitude, B magnitude down to 16, and they reach distances of up to 10 kiloparsecs, which is enough for we want to evaluate. Now I'm gonna spend a bit of time in this diagram. So in this color magnitude diagram, we are displaying basically our sample and the one and the stars that are from the ALS3 catalog that we have not observed. And our sample is separated into two, in the stars colored in blue and the stars colored in green. So to separate them, basically, we use the following. Here you have the 20 solar mass track, and basically O-type stars, they are typically born with these masses, with 20 solar masses. And we wanted to find which is more or less the point in which they transition into P-type supergiants, which is somewhere here. If we want to evaluate the location of the end of the main sequence within the B-type supergiant domain, then we need to look for the completeness level of this group of stars here. And to that direction is basically the extinction, which already shows something which is, to me at least, interesting, which is that already all the stars are at least one magnitude extinguished. I mean, ideally, if without extinction, all these stars that we see here, they would fold into this region. But you can see that when limited to magnitude 11 and 4 kiloparsecs of distance, we reach even 4 magnitudes of extinction. Now, we did the best we could to do the one-to-one comparison with the ALS3 catalog, and what we obtained is this table that I show here. So here, for 4 different distances, up to 4 kiloparsecs, and for different limiting magnitudes, we see our completeness level, the total number of stars, and our completeness level. So for bright stars, we basically account for all of them up to 4 kiloparsecs of distance. But what is interesting is the last one, because we said that, okay, for magnitude 11, we can afford several magnitudes of extinction, as long as we are staying within 2 kiloparsecs, 3 the most. So we see that, okay, for 1 kiloparsec, we are basically complete. Then the number of stars that we have starts to decrease, 77% for 2 kiloparsecs, 62% 3 kiloparsecs, and a bit more than half for 4 kiloparsecs. Now, what we decided is to find a compromise between volume and number of stars, and completeness, of course. So we decided to take 2.5 kiloparsecs as our compromise between all these parameters. So we account in up to that distance with 70% of the stars. And it is within that volume where we want to analyze, or where we want to find the end of the main sequence. Now, one thing is, of course, if your completeness is very high, but the volume is too small, then maybe you are actually accounting with features that are intrinsic for that part of the galaxy. So you cannot go to very small volumes. You need to increase the volume enough so that you actually account for like stars that have the different origins within the Milky Way. So we adopted that distance, we adopted that sample size, and I'm going to represent it now in the HR diagram. So in this first HR diagram, I'm limiting the sample to stars within 1.5 kiloparsecs, which corresponds to the stars that are analyzed within this circle here. And I have separated the stars into 2 colors. Those that are rotating above, or they have a projected rotational velocity above 100 kilometers per second, are colored in this cyan color, and the rest are colored in orange. And I have also created this kind of density mesh to show a little bit, so that you can see qualitatively which is the distribution of stars. But the one that is important for us is the one that involves stars within 2.5 kiloparsecs, which is this one here. So here, we already see the feature that we are interested in, which is a decrease in the number of stars below a given temperature. So we kind of see that in this region, we have significant, or at least apparently lesser number of stars than in this region here. And just to put all of them and show it to you as well, if we use all the stars in our sample, this is how the HR diagram looks like, which doesn't show like significant differences, but we already know that here biases are likely to exist, so we are going to stay with the central panel. Now, in order to better describe the drop in the number of stars, what we did is to translate these 3 HR diagrams into histograms. And if you have already noticed, we have like 4 kind of ranges of luminosities, 4 luminosity ranges. And what we do is to translate these 4, 4, and 4 slices into histograms, which is this figure that you see here. So if we look at the middle panel, we see that indeed there's a drop that we can detect. And what we did here is to use the cumulative distribution function to kind of define the position of this drop. What we did is to see where the cumulative distribution function of stars that we have starts to flatten. And we found that we achieved this flattering when we already get around 85% of the stars from, let's say, the beginning of the main sequence until that point. So actually, I'm going to show it better here. So when we account 85% of the stars from hotter to cooler temperatures, we get these four kind of values of the temperature that we use to define our proposed terminal age, updated terminal age main sequence, where that we have also described, well, analytically, like with this expression. So you can see now the location or our proposed location of the end of the main sequence in the HR diagram. And now I'm going to go all the way to the beginning. So this, if this is the actual end of the main sequence, it implies that many B-type supergiants are actually main sequence stars. Not all of them, because here more or less it's like B2 spectral type. So not after that spectral type, but B0, B1, and many B2 type stars are actually, according to this, still main sequence objects. But this is not the only let's say, observational feature that has been proposed as empirical clue to find the location of the end or the terminal age main sequence. So again, I'm going to go back in time to the work by Howard in 1997. They found a feature, which is that if you look at the projected rotational velocities of massive stars, and you evaluate which is the highest vsini values that you obtain, you see that as you go to cooler spectral types, there's a moment in which you observe a drop. So it goes from more than 200 kilometers per second of projected rotational velocities, and then it drops significantly down to 60, 70, something like this. This feature is now well known. I mean, it has been found by different groups. And actually, I'm showing it to you in this recent paper that we published last year that uses essentially the same sample that I presented before. So is it like all the luminosities? I mean, it's all the stars within the same range of luminosities, but same group of stars. And you actually see this drop. Now, this is the drop that has been proposed to indicate the end of the main sequence. And following this argument, also these stars that we see here would correspond then to possibly products of binary products or products of binary interaction, or possibly also stars that are returning from a later stage. For example, the red supergiant, after reaching the red supergiant phase, they're returning and they have, they have lost all this angular momentum and then they are rotating slow, but they are no longer main sequence objects. So since we have this nice volume limited sample, we wanted to actually see where these fast rotating stars are with respect to our proposed end of the main sequence. So what we find is, well, I'm going back to the previous plot, and now you actually understand why I was separating stars into these two groups. Now looking at the fast rotating objects, if we look at the center of the HR diagram, we see that indeed beyond this proposed end of the main sequence, there are not many, or there are no fast rotating objects. Now we play a simple exercise of calculating the ratio between the number of stars before the TAMS and after the TAMS, as also the proportion of fast rotating objects with respect to the total number, to kind of see or, well, calculate a little bit in an easy way, which is the number of fast rotating stars that we would expect after these TAMS, and which is about 6, which is not much. I mean, it's actually a very low number. So the chances that we observe these 6 stars, it's relatively low. So what we found is that through this argument, it could be one possibility is that the lack of fast rotating stars may be simply explained by dropping the relative numbers. So we actually don't see them because the chances to observe them are quite low. Now, some of you may have already spotted that, yeah, this is fine for this region, But for these two regions, the situations are quite different because here you don't have many, only two fast rotating objects before the end of the main sequence. And then here you have a lot of them beyond the main sequence. So how can we explain this? So what we came up with, or what we found like as a potential explanation for this, it connects the rotation, well, actually connects this distribution with the fact that stars may reach their critical rotation. So for this, what we did, or to evaluate this, what we did is to, again, separate our stars into the same four slices of luminosities, which is what you see here, these four slices. And again, show the vsini against effective temperature distribution. And what we did is to pick the nearest evolutionary track and represent the critical velocity. The next thing that, well, that you can see here with this green line for the four luminosity ranges. The next thing we did is like, okay, let's see more or less which is the average vsini value of the fast rotating component of our distribution. And on average, more or less, they have around 230 kilometers per second. This one here. So we represented this value in this evolutionary, well, in these tracks, or in these limits of critical velocity. And we did, I think it's a second order polynomial fit to these 4 points. And this is what we got. So for at least for me and for us, like it was quite representative that it follows really well the distribution of, or let's say the position of the coolest fast rotating objects, which led us to kind of conclude that it could be that it is this critical velocity, the one that limit the presence of fast rotating objects. So it can be partially explain the end of the main sequence, but most importantly is limited by this fact. Now, this is one thing, but you may have also noticed that, fine, but here you have a lot of fast rotating objects that are located beyond your proposed TAMS. And it's quite, I mean, it's a very large number compared to the other stars, the other B-type stars that are rotating below 100 kilometers per second. So we also wanted to find a potential explanation of this, a larger number of fast rotating objects. And for this, we went into evolutionary models. And when you look at them, for example, these models by Broad 2011, you see that rotation impact affects the extension of the main sequence. And in this range of masses, what it does is to extend the width of the main sequence to cooler temperatures. So we find this as a potential explanation of this larger fraction of fast rotating objects. Now, there's another thing that I find quite interesting, and is that while creating this plot, I was curious to mark those stars in which I observe this kind of double subpeak structure in the H alpha profiles that could be an indicator of a disk. And a disk that is formed because these stars are actually reaching their critical velocity. And what we found is that indeed, in many cases, all these stars that are close to their critical velocity indeed have this double subpeak structure. That to me, it supports the idea that this is the reason that it's limiting the observation of fast rotating objects. So I'm gonna move now to a third empirical feature that can help us to find the position of the end of the main sequence. And this involves the binaries, spectroscopic binaries. In this case, I'm using the reference work by McEvoy et al. 2015, that they were analyzing a group of massive stars in the Tarantula Nebula. Here they represented stars into kind of, well, 3 groups. They represented those stars observed or detected as single stars, those detected as binaries, and those that are like farther away and kind of isolated that they consider helium-burning objects, therefore not in the main sequence. So here the argument is that if you have a binary system, the chances that you are going to have a binary system which the two masses are very similar, and then maybe you have a system that evolves as a binary all the way out of the main sequence, are low. Typically, you have one star that is more massive than the other, and then this star will, the one with more mass will evolve faster, and then it will eventually merge with the secondary, or maybe it will just explode, kick out the secondary, and then you are not gonna longer see the binary system. One way or another, I mean, there are arguments to say that the chances to observe binary stars beyond the main sequence are lower. And this is exactly what we wanted to check within our sample. So to check this, we aim at finding spectroscopic binaries. Single line spectroscopic binaries first. So to do this, we measure radial velocities. Well, I forgot to mention, but within the IACOB project, we also observe, I mean, we have multi-epoch data. So for enough stars, we have at least 3-4 spectra. So we are able to actually measure the radial velocity shifts in the case that are produced by a companion. They would look something like this. So what we did is to take all, again, within the 2.5 kiloparsec volume, we took all the stars for which we have 3 or more spectra. And within those stars, we saw if the shift that we observe is corresponds with an SB1 system. Here, the detected SB1 system are shown in green color, and you actually see again that the number of, qualitatively, the number of objects or SB1 system is lower beyond this empirical TAMS. To put it in numbers, because of course we have to put it relative to the total within the main sequence and outside or after, we account for 40% of SB1 system within the main sequence and only 15% of SB1 system beyond the TAMS. So indeed, there is a drop of SB1 system as we cross this line that could, again, support the fact that the location of the main sequence should be somewhere here. The side result is that we also observe that the fraction of SB1 system decreases within the main sequence. So we account for more SB1 system in the O-type star domain. And then this number is reduced to around 35% within the B-type supergiant domain, which is actually the first time that it's been shown for Milky Way stars that are in the fields and clusters all together. So this is also supporting the location of the TAMS, but we wanted to go one step further, and we also wanted to look at the SB2 system. Now, I said at the beginning that I excluded SB2 system from our sample because we cannot analyze them. But still, what we can do is to check for the spectral type of the primary component and see, well, where we find less SB2 system of this or that spectral type. And what we found is that also for SB2 system, we find an important drop or decrease in the number of this object as you cross the empirical TAMS that, as I was saying before, it's somewhere around B2 spectral type. In this case, in the middle panel, I am showing the number of stars of SB1 system as a function of the spectral type. So I just did this to kind of compare it with the one on the left. But of course, here we have the temperatures as I'm showing here. So also for SB2 systems, we find this drop in at this position. So bottom line, until here, we found important clues on the location of the terminal main sequence in the massive star domain. We have found a drop in the relative number of stars, which is an important improvement with respect to the work by Castro et al. 2014, for all the reasons that I mentioned. For the completeness, we are using Gaia distances, a larger sample, homogeneous results. I mean, they have been analyzed homogeneously, and all this aspect that we accounted for. We also found a drop in the relative number of SB1 system, which is, I mean, in terms of number of objects, it's an important improvement also with respect to the work of McEvoy. That this drop can also support the location of the terminal main sequence. And we also found the drop of the fast rotating object that, as it is, we believe that it could be better explained by stars reaching their critical velocity. So this is the summary until here. But we obtain more things that are actually relevant to improve our evolutionary models, because at the end, what we want to achieve is this. We want to help to find new answer points that can help future evolutionary models to better describe the nature, right? So I'm going to compare now with different evolutionary models, state-of-the-art evolutionary models, or some of them. Here I have two plots. On the left, I'm plotting evolutionary models from Ekstrom, from MESA, from Broad. And all of them, they have solar metallicity and for no initial rotation. And on the right-hand side, it's the same models, but I am plotting those models for 0.4 of the critical velocity. And similarly to what Castro did, we are also including this mesh, this density mesh, to see which is the distribution of stars. Now, on the left and on the right, I have included an additional empirical end of the main sequence, accounting on the left only for stars that rotate below 100 kilometers per second, and on the right, only including stars that rotate above 100 kilometers per second, so fast rotating stars. So what we describe in this paper is basically, well, we did like a qualitative comparison between the models of the observation. In both cases, we observed that, or basically in all the models, we find quite a good agreement as it was in the work by Castro. When you go to initial masses below 15, more or less, but then as you go to higher masses, the situation, it's not so good, particularly for those models of Ekstrom and MESA, as also for Broad for higher masses. Although for the models of Broad, the agreement is quite good in this, let's say, middle range of masses. Now, when you move to models with 0.4 of the critical velocity, as I said, the agreement is good for lower masses, but then interestingly, we found a good agreement with those of Ekstrom 2012 that kind of, well, reproduces more or less what would be the situation if we would only account for fast rotating stars. So this is the comparison. I invite you to read the paper to check a little bit more about this. But what I wanted to show you, as now that I have a bit of time, as an illustrative thing, is how by adjusting the input parameters of the evolutionary models, you can really change the shape of the evolution, or at least the location of the end of the main sequence. So again, as an illustrative thing, I am including these plots that I have taken from the work of Martinet 2021, in which I am showing the evolutionary models for two initial masses, 9 and 25, and I show you here how the core overshooting, which can significantly increase the width of the main sequence because it adds fresh hydrogen into the core, so it can be burned and extend the main sequence. So how this core overshooting parameter can significantly extend the main sequence, and the same thing for higher masses. These models are, by the way, not rotating models. And my goal now is basically to do something similar to what Martinet et al. Did in 2021, to actually put this in practice and improve the evolutionary models that we have nowadays. There's another thing which is important, which is rotation. Rotation also affects the evolution of massive stars. They affect the luminosity, the temperature, the surface composition, and of course also the width of the main sequence. So to illustrate this, I have included also from the work of Martinet 3 no rotation, another one with 0.4 of the critical velocity, and another one with 0.4 of the critical velocity. You can see here how, again, changing the initial rotation combined with different core overshooting parameters, you can get very different positions for the end of the main sequence. So this is, I mean, yeah, this is basically what has to be fine-tuned in order to reproduce the observation. There are other processes that can also affect the width of the main sequence. And of course, this is like, well, out of my scope, but it's something that I want to highlight. But I want to go into the topic of rotation. So what we observe, I'm going back to this plot that I showed you before, in which I am showing vsini against effective temperature. And there's a lot of information here. So one of the things that one can spot is that the majority of the stars that we are showing here, they are rotating slow, below 100 kilometers per second. This could actually tells us that massive stars in this regime of masses are born with slow or mild initial rotation. It doesn't mean that all of them are going to be born with slow rotation. Maybe some of them are born with high rotation. But the fact that the majority of stars have this slow rotation can indicate this. We also see that for both components, for the fast rotating component and the low vsini component, there's like the average or the mean of the velocity slowly decreases with decreasing temperature. This can tells us that there's a slow surface breaking occurring along the main sequence. Stars are not slowing or spinning down very fast, or there's an important or efficient angular momentum from core to the surface that is compensating this surface break. Likewise, this is an important also empirical constraint for evolutionary models. Now, this, I mean, because I haven't said anything, and probably some of you are already like, but say it. There's the question of which is the evolutionary nature, which is the nature of fast rotating objects. So as it is now, there's a growing belief that fast rotating objects result from binary interaction, and it is through mass transfer, for example, that they can spin up, and then that's why we observe them. And it's not like stars are born with such high rotation. It's not, it may not be impossible, but this is the a growing belief nowadays. And I want to be also critic regarding our results, because just as I showed with the case of fast rotating objects that may have their origin in binary interaction, I mean, it can happen, and it's likely to occur, that our diagram is populated by products of binary interaction, and this may or may not follow like the single evolution scheme that until now I have followed all the way until here. So it means that our sample is likely contaminated by these products. It could be contaminated by mergers that may alter or likely alter their evolution. It could be contaminated by post-mass transfer objects. It could also be contaminated by stars that are evolving blueward. So this, of course, needs to be accounted for, and this is, in my opinion, one of the more important topics that massive star community needs to solve. But they are there, and in order to get a definitive answer, at least this needs to be answered sooner or later. But I also want to be critic with the stars that I have not included in my sample, because of course they are there, and maybe this was actually one of the questions that you have, but I'm going to mention them. So we have stars that we have not observed, and if all of them would be evenly distributed in the spectral types, then no problem, because you are missing the same number of stars per spectral type. So in order to test this, we did this plot here, this histogram, where we are showing the percentage of stars that we have observed relative to the total as it is listed in the LS3 catalog. And here you can see that the spectral type where we are missing more stars is B0 spectral type, which corresponds to a region that is somewhere here. You may have already noticed by now that here there's kind of an underdensity of objects. And one potential explanation of this underdensity is because still we are missing stars in this region. We are also not accounting for hypergiants, but hypergiants would be located somewhere here. Unfortunately, we don't have the tool to derive reliable parameters there. Same thing for B stars, although we expect them, or the classical B stars, although we expect them to be in the bottom part of the diagram, we would not expect it to affect too much into our results. And there's also the SB2 stars that, since we are not doing spectral disentangling and then analyzing each of these spectra individually, we also don't, I mean, we don't have them in the diagram. And in this regard, it is known that within the O-type star domain, there are many SB2 systems which are not shown here. So of course, this part of the diagram is in that regard biased. More specifically, late O-type stars, 09.5 or 9.7, they have more SB2 system compared to the others. So both of these, the fact that we are not accounting, or we don't have that many B0 type stars as we would like, and the fact that SB2 systems populate here and they are not represented, may actually fill this gap that we observe. So this is what I wanted to show you. Actually, before the conclusions, I'm gonna, since I also have a bit of time, I would like to, I mean, I have a lot of hope in this, so I would like to mention a little bit. So now with IACOB, we have reached, say, up to 2.5 kiloparsecs. And we have obtained these interesting results that, of course, can help to improve our evolutionary models. But I mean, the future is really promising, because now we have two incredible surveys. We have for most formidable low resolution OB survey, and we have the WIF skip OB survey, both of which are basically going to overlap perfectly with the sample of IACOB. So we can extend and reduce even more the biases that may exist in this volume limited sample. So we can actually improve even more the our vision of massive star evolution, or these features that I have shown through the presentation. And to conclude, I have listed a few key points. So we built the largest and most complete high-resolution spectroscopic sample of galactic luminous O3 to B6 type stars to date, which is a significant, very important step forward in different aspects with respect to the work, our reference work of Castro. We use this drop intensity of stars to define the location of the terminal age main sequence for masses between 12, or initial masses between 12 and 40 solar masses. And in contrast to the classic interpretation, our results suggest that a large fraction of B-type supergiants would still be on the main sequence. Then we interpret the scarcity of fast-rotating objects on the cool side of the TAMS as the result of stars reaching near critical velocity and from the proportional decrease of fast-rotating stars when crossing the TAMS. We obtain a drop of 25% in the number of SB, or relative number of SB1 systems when crossing the TAMS, which we consider as an additional empirical clue of the location of the TAMS. And we also found similar qualitative behavior for the SB2 system. We found a larger fraction of the low vsini stars, which may indicate that massive stars enter in the main sequence with low or mild initial rotation. And this would be compatible with the assumption or the growing belief that fast rotating stars mainly result from binary interaction. And last, and I would say more important, these results can provide strong empirical constraint to improve future Abel train models. And that's it from me. Thank you.
All right. Thank you very much, Abel. Everyone can join me in congratulating you on a very nice talk, and especially really nice work, very, very meticulous. So at this point, we'll be taking questions. Does anyone have a question for Abel? Yes, yeah.
Hello. Yeah, I saw that you were playing with the overshooting parameter. We have also looked into some binaries here, and we do have a kind of similar conclusion, meaning that we have an increase in the overshooting parameter needed to explain what we have for the structure of the star. Which we measure through apsidal motion. So my question is, have you looked into those results, and or do your needed increase in overshooting compared to that needed from other type of diagnosis, just as apsidal motion, but not only? I think people from asteroseismology also needed this kind of increase in overshooting. So is it compatible values, compatible increase, or do you need more or less?
My micro, yes. So, well, this is actually something that it's what I want to dig into now, to this kind of comparisons. We need it, in general, we need higher core overshoot parameters. I personally believe that, I mean, it could be that it's mass dependent, and it has been proposed in the past or several times. But yeah, I mean, this is the kind of thing, I mean, I haven't looked into it, but I definitely want to. And this is actually one of the things that I want to do within my postdoc, to actually dig a little bit more into the theory. So, but thanks for bringing it, because, yeah.
Okay, then we have Yurik.
Hi, Abel, very nice overview of your work, very meticulous indeed. I have nothing against the reaching of critical, nor that the TAMS might be in that area, but I still don't think it explains the sharpness of the vsini feature at the temperature 22,000. You would expect that to be more gradual, I think. If you reach the TAMS, I don't see why it should be so sharp at that. Have you any thoughts on that?
Yes, actually, I believe that it is actually the effect of binaries, and actually, I strongly believe it. and it's something that I actually want to present in the Munifest, but we observe enough stars in that particular region, especially in the higher masses, that have strong indications from the chemical compositions to be binary products, which means that if I remove those, then the TAMS for higher luminosities would shift to hotter temperatures. So it would be more like diagonal. So I believe that one potential reason for this is actually the presence of binaries. But of course, I mean, the final answer would be after the whole analysis of the chemical abundances is done, at least for our sample, our complete sample. But I also noticed, I mean, actually, well, I was like preparing the presentation, I was still like looking at this figure in which if you actually remove, I mean, if you don't account for fast rotating stars and you are just looking at this, I mean, of course, there's the possibility that some slow rotating stars are also products of binary interaction because magnetic fields or something like this. But if I remove those that could, I mean, those fast rotating stars that let's assume for a second they are coming from binary interaction, then this drop, it's even more like vertical. I mean, this is basically fixed at 22,000 Kelvin. Is the red line here. So indeed, I mean, I was just preparing this and I was actually pointing to the same thing that you mentioned. So yeah.
I think
also, well, one more thing, just sorry, like also there's the other thing that, as I was mentioning at the end, there's also a difference in, let's say, completeness between the O-type stars and B-type stars. And if you put more stars here in this hole that I was showing, then again, all this would shift a little bit to the left. So it's likely that it's more like diagonal that we see here, more towards hotter temperatures. But I still, I mean, I agree with you that to me, this still looks very vertical.
Right.
Yeah.
Yeah, no, I agree with you that it's quite possible that a lot of these fast rotators are binary products, but then I would still like to understand why that would create that feature so sharply over such a mass range.
Mm. Mm. Mm.
Food for thought.
Thank you.
All right. Are there any other questions for Abel? So yeah, I think there's some good discussion starters and maybe some good talks to be had in the Canary Islands in a couple of months. So this is all pretty exciting stuff. So Abel, thank you once again for this really nice presentation. And for everyone, I'll mention that fairly soon we'll be announcing our next talk that will be occurring in March. And yes, once again, let's thank our speaker for a wonderful talk. So stay posted for the details of the March talk to be announced soon. And otherwise, thank you so much, everyone, for connecting. Thank you, Abel, for the presentation. And we'll
Thank
be
you,
seeing
Alex.
you all pretty soon. Have a great rest of your day.
Have a nice day too. See you next time.
See you.